Hello everyone, I'm Leo, a PhD student in the eye for medicine and healthcare at Technical University of Munich. Today I'm excited to share my research with you, a paper titled Propagation and Attribution of Uncertainty in Medical Imaging Pipelines, which I collaborated on with Martin, Kerstin, Paul, Wenqi, Daniel, Rickmer and Georg. In the realm of deep learning for medical imaging, we often encounter complex pipelines where the output of one model becomes the input of another. These pipelines can be quite extensive, involving multiple stages such as reconstructing medical images from undersampled case-based data and subsequently perform classification tasks. Therefore, they can vary in length and include one upstream model followed by multiple downstream models. In medical imaging, it's crucial to understand how confident a model is in its predictions. Bayesian models have proven to be valuable tools in this regard, as they not only provide a mean prediction, but also an uncertainty estimate. A prime example is Bayesian MRI reconstruction, where the model offers not just a single image prediction, but also an uncertainty map. However, our focus was primarily on aleatoric uncertainty. But integrating these Bayesian models into medical imaging pipelines is not straightforward. Some approaches concatenate the mean and the uncertainty predictions as channels and use those as input for the downstream models. However, in such a setup, quantifying the influence of the upstream uncertainty on the overall uncertainty of the pipeline remains a challenge. To address this, we developed a method to propagate the uncertainty from the upstream model through the downstream model, allowing us to get the propagated uncertainty at the downstream uncertainty and calculate the joint uncertainty of the pipeline. Those pipelines can have an arbitrary length. Therefore, we chose to interpret the output of the pixel-wise regression upstream model, including the mean image and the variance map, as normal distribution, and perform Monte Carlo sampling from this distribution. For every sample, we execute a forward path of the downstream model to get samples of an intermediate representation. Thereafter, we can calculate the joint uncertainty for both downstream regression and classification models. For downstream regression pipelines, uncertainty is determined by a variance that combines the upstream uncertainty with a delta introduced by the downstream model. On the other hand, for downstream classification pipelines, uncertainty is represented by the entropy of the categorical distribution, with the contribution of the upstream model being defined by the mutual information. To validate our method, we applied it to real case-based data from the fast MRI dataset, where we classified the knee side as a downstream task. We also experimented with synthetic case-based data, where we predicted brain volume using single slices. In both cases, we introduced various levels of undersampling to inject noise into the data, thereby contributing to the data uncertainty. Our results clearly demonstrate that higher undersampling rates correlate with increased upstream uncertainty, which, after propagation, leads to a greater propagated portion of the downstream uncertainty. This trend is evident for knee classification and for brain volume regression. In summary, our research showcases the feasibility of propagating uncertainty through medical imaging pipelines and aggregate the uncertainty while providing insights to the contributions of the individual pipeline components. Looking ahead, we plan to expand our method to incorporate spatial correlations between pixels and fine-tune the calibration of the pipeline. Thank you for your attention.